And we're live. So, hello everyone, and welcome to our November edition of the Astronomy on Tap in Cambridge. And today we have a fantastic evening full of information on, if you will, our cosmic backyard, the solar system, through meteorites delivered to us by our wonderful speaker, Craig. But before we get there, let us quickly introduce ourselves. Annabelle, let's start with you.
Hi everyone, I'm Annabelle. I'm a second-year PhD student at the Institute of Astronomy in Cambridge. I'm studying galaxy clusters and black holes at the center of them.
Thanks, Annabelle. Next up, we've got Johnny.
Hi, I'm Johnny. I'm a second-year PhD student also at the Institute of Astronomy here in Cambridge. I study terrestrial planet atmospheres and their interiors.
Fantastic. Hayley?
Hello, my name's Hayley. I'm a postdoc here in the maths department at Cambridge, and I like cosmology and general relativity.
Awesome. A couple words about myself. I'm your technical MC for today, which means I'm running this show. So if anything breaks down, you know who to blame. I am a PhD student studying at the Kavli Institute for Cosmology, studying galaxy evolution and in particular galactic death. But without further ado, let's leave the floor to our fantastic speaker for today, Craig. If you don't mind saying a couple words about yourself before you go on.
Yes, great. It's a good introduction, strong billing. It's great to be here. I'm a third-year PhD student in the Department of Earth Sciences, studying meteorites, as you probably could have guessed, and planetary science in general. So I'll share my screen so we can launch into the talk.
Yep.
Okay, here we go.
Fantastic. Yep.
Great.
Fantastic.
So for my talk, I thought I'd do something perhaps a little different to what's happened before by trying to describe what it's really like to do science. You know, I think people know about the number crunching and the analysis we do, the brainstorming, but there's actually lots of unpredictable things that happen during a life in science that you might not think about going into it. So this talk is about meteorites and my work on them, but also a behind the scenes of life in science. Okay, so by definition, you know, what are meteorites? And by definition, they're not from Earth. Meteorites are rocky objects that originated off-world and at some point fell to Earth. Most meteorites are incredibly old, some of the oldest solar objects in the solar system, in fact, and they're also very diverse. We found such crazy things as tiny mineral grains that were forged in supernovas before the sun even formed, as well as lumps of iron metal that were once part of the cores of planets that no longer exist. And you can get a sense of this extraordinary diversity from these different images here. Don't expect to know what's going on immediately, but hopefully by the end you'll have a better idea. But we found meteorites that come from the moon, from Mars, and from a bunch of different types of asteroids, representing most of the different types of rocky objects that we find in the solar system. And the images I'm showing here are really just scratching the surface. It turns out that space is a complicated place. So, how do we know what meteorites are? I mean, the easiest way to get into this is to tell you about the history of the solar system, because really that's what meteorites are sampling. Ultimately, they're just rocks from space. But the easiest way to think about it is this diagram here, which I put together from one of my papers that shows the history of the solar system. And so ultimately, you start with a nebula of gas and dust that slowly collapses in on itself. When the pressure gets extremely high at the center, you can start some nuclear fusion and you get a star going. So that's the birth of our sun. And the material around the sun that's left over forms a disk that orbits that we call a protoplanetary disk. The meaning behind that name is simply that it formed before the planets, and the planets formed from the material that was in this disk. And you can break down the material into various different types in terms of how close to the sun it was. So closer to the sun, you have something, material that went on to form asteroids called chondrites. This is the material that went on to build planets. And the interesting thing about this is if you look at the material, it changes its chemistry depending on how close to the sun it was. So elements that boil off more easily at lower temperatures, there's less of those the closer to the sun you go in the nebula, and less of them ends up in rocks that form there. So you can divide the meteorites up by how close to the sun they formed. And that trend extends right out to the edge of the solar system into the comets, which are perhaps the most well-known of all the space rocks. And they're just balls of ice and dust that burn up as they get to the sun, which results in these magnificent tails, like in the image I'm showing on the left here. And despite being perhaps the best known space rocks, they're also the most elusive for us scientists. because they burn up so easily, just mostly being made of ice as they approach the sun and as they crash to Earth through the atmosphere. So there's barely been any cometary material actually sampled in meteorites, apart from a very few tiny pieces. If you want to go and get some cometary material, you really have to send a robot, a space mission to go and do it directly, which is happening with missions like Hayabusa. Very interesting stuff. So combinations of comets and chondrites, these balls of ice and dust and rock, come together in larger and larger amounts under gravity. They form planetesimals, the division being that when they get to a certain size, they're producing enough heat that actually they start to melt. They have magmatism and volcanism, something a bit more like a planet. And from that, we start to call them planetesimals, things that could form planets. And again, more cosmic pinball, they crash into each other, get bigger and bigger and bigger until you start to build the planets, like, for example, Earth right at the end. So maybe now if I go back to this picture, all the different meteorite types, it will start to make a bit more sense. You know, we have the earliest formed asteroids, the chondrites, various different types depending on how close to the sun they formed, how much water and other volatile elements you can divide them up by. And then you have things that form planetesimals and protoplanets. One at the top here is the HEDs. They're from a large asteroid we've actually identified called Vesta. And they come from its surface, its crust. The Earth has a crust just like this large asteroid. There's other meteorites called pallasites, and they're a mixture of the silicate minerals that form these crust-type meteorites and iron from planetary cores, and they sample the barrier between the crust and the center of a protoplanet. And finally, we have iron meteorites, which represent the once liquid iron-rich cores of these protoplanets. And the reason we have them is because at some point, these things have been destroyed and pieces scattered out all across the solar system. So that's how you could possibly have the piece of an interior of a planet. And then finally, we have pieces of the planets themselves and the moons from Mars and from the moon. And they get here when another asteroid slams into the surface, kicks pieces off into space, and at some point, a piece finds to Earth. So yeah, sampling most of the history of the solar system here with meteorites, and that's why they're so useful. So the key thing is to recognize is that whilst I've explained to you here, hopefully everybody's still following, in about 5 minutes, what all these different meteorites are with the help of, you know, a figure of solar system history, the reality is that it took scientists decades to figure this stuff out. They didn't have the answers to work back from. All we had were the rocks themselves. And yet somehow they were able to extract all this information from the meteorites. So the question is, you know, how do you go about doing that? And there's really 3 key things that a geologist thinks about in studying meteorites, which is how old are they, what are they made of chemically, and which minerals do they contain. And the reason this is so, you know, crucial and allows you to work things out is if you know how old something is, then you can start putting them in sequence. You can be like, this meteorite was much older than this one, therefore these later meteorites may have formed from the previous ones in some way. You can start to tell a story about which meteorites came first and later. By looking at the chemistry, I described to you earlier, you know, we think that these things form at different distances from the sun. If you measure the chemistry of these things and find out how old they were, and then talk to the astronomers, the cosmologists about what they think the solar system should have been doing, you can work out that, oh, the models predict there should be more water further away from the sun. This meteorite has more water than the other one, therefore it formed further away. So you can start to stack these rocks up in terms of how old they are and where they formed. And finally, the minerals are absolutely crucial because we can make the minerals in the lab. We can take, you know, the bulk chemistry of a meteorite, put it in a furnace or something that applies pressure and play around until we actually make exactly the same thing. And therefore you can work out exactly how the meteorite must have formed when it was out in space. And the other cool thing is you can look at whether or not the minerals are pristine under a microscope. You know, have they been deformed at some point? If they have, then that tells you that maybe this meteorite participated in a collision when it was out in space. And that can start to tell you about that cosmic pinball of things moving around in the solar system. So that's how geologists work things out. So now we know roughly what meteorites are and sort of how we know what they are. And for the rest of the talk, I'm going to chat about what I've been up to in studying the wonderful world of meteorites. Our story begins in 2016. Lots of things happened in 2016. Andy Murray won Wimbledon and I went to watch, and some other things happened as well. Not so good. Some of us are still going strong. That's me. Other of us are not doing so good at the moment, which is good. So the question is, how do you end up trying to work on the origin of the moon with meteorites? And the answer is that it's dumb luck. You don't just wake up one morning and think, right, I'm going to dedicate the next 4 years to working on meteorites. So it was literally luck. I was assigned, third year undergrad at St Andrews. That's where I studied before at Cambridge. Just had to do a group project, a poster, my first scientific poster, read a paper and tell the lecturers about what the paper was suggesting. We could pick anything. And so I just looked at papers that had come out relatively recently, and this one happened to catch my eye by Yin et al. That was talking about the moon forming impact and relating that to chondrite meteorites. And the reason this is so interesting, go to the next slide. I mean, maybe some of you have heard of this idea, maybe not, that the moon formed in a gigantic collision between Earth, proto-Earth, and something about the size of Mars. This is our best guess. And the reason we think this is that the moon and the Earth, surprisingly, although they might look different to the naked eye, if you go and measure the chemistry, they're identical. And to get two weird objects orbiting each other with identical chemistry, the easiest way is to take two different objects, smash them together, and mix them up so that they end up with everything averaged out, like pouring together two cake mixtures and then taking two pieces from that. So you average everything out. And this is an artist's impression of what this event might have looked like. Probably the most, cataclysmic thing to ever happen in our solar system, and pretty spectacular. But this is based on chemistry and physics, but we don't really have any evidence, physically that this happened. But the Yin paper, what they were suggesting, was going back to this idea of cosmic ping pong. They said, okay, we have the Earth. It gets smashed into by something about the size of Mars, which ultimately goes on to form the moon. But pieces of this escape Earth's gravity and fly out towards the asteroid belt, which is represented by these circles out beyond the orbit of the Earth. And they crash into some of these asteroids, the chondrites I was telling you about earlier. And maybe they leave a record of having done that, which is something we can study with meteorites. So for example, here's a picture from some of my work showing a heavily deformed mineral, something that participated in one of these massive collisions. And to explain the image on the left, the light and dark gray are different minerals, phosphate minerals. The darker gray one is called apatite, which is the same mineral that makes up your bones, actually, weirdly, but it's also found in meteorites. And the light gray at the bottom here is a mineral called tuite, which is the same thing chemically, but it forms at much higher temperatures and pressures. And you can see these white lines, like fractures, going through the darker gray apatite. When I studied this with microscopes and different types of chemical analysis, I realized that was actually thin veins of the tuite going through the apatite. And what we're essentially seeing here is a grain of apatite caught halfway into turning to something else. And the only way this is possible is if this grain was subjected to extremely high temperatures and pressures very quickly, but then those temperatures and pressures shut off almost immediately. So you can imagine you've got your asteroid going through space quite happily, something else smacks into it and heats it up, puts it under immense pressure, and the minerals start changing. But then the two pieces drift apart again, you're in space, everything cools down immediately, and the process doesn't finish. So what this is essentially showing is direct evidence this meteorite experienced massive pressures and temperatures, but only extremely briefly. So using minerals, you can get proof of the histories of these objects. And the Yin paper, the thing that they did that was really important is they took exactly the same type of grains they found in a different meteorite, and they worked out how old these things were when they got deformed in this way. And they found that it happened about 4.45 billion years ago. That's a long time ago, but it's also exactly when we think, don't know, but when we think the moon formed. And actually they added this to a list of meteorites which had identical, minerals like this that were highly deformed, and everybody had found the same age, 4.45 billion years, about when the moon formed. So to go back to the previous slide, they come up with this idea, maybe this is because pieces ejected from the Earth and the moon smashed into the asteroids out here and preserved these textures and these ages. So that was the hypothesis they were working on. And I essentially talked about this in my poster No research at this point, just talking about it in the class assignment to the staff members. Dr. Sammy McHale here. I'd never actually met him. I just knew he was in the department, and I knew he did planetary science. So I sort of went over to him at the start of the poster session and said, right, I want to tell you about my poster because I thought that would be fun. And we had essentially the chat I just talked to you now. I told him all about the Yin paper and what they thought, and he thought that was fun. And I thought that would be that, I've done my assignment. But little did I know he was going to get a phone call randomly a few weeks later from one of his colleagues who works on meteorites, Dr. Mahesh Anand, asking if he had anyone interested in meteorites who might want to do an internship with him to do some actual science. And so he called me up and said, Craig, do you want to do this? And I said, yeah, absolutely. I was kind of jaw dropped, but yeah, it was a fantastic opportunity. So I took him up on it. And I ended up going to the Open University down in Milton Keynes, which, as it turns out, has a physical campus that's one of the best for planetary science in the world. And some of you in the audience may have heard of the Open University, and I'd only heard of it in the context of online learning, but actually they do have one of the best research facilities on Earth. So that was kind of mind-blowing, and it was very exciting to go there. And here's me arriving in front of a building that bizarrely is called Walton Hall. My name's Craig Walton, so it kind of felt meant to be, and it still does, because I had a great time. Had a really fantastic time learning about meteorites and how to study them. Mahesh, my supervisor, told me, don't worry too much about trying to do new science while you're here. You don't know anything yet. Just watch and learn, and try and pick up as much as you can, and we'll see what happens. And so that's essentially what I set about doing, just reading a lot and getting hands-on with the meteorites. And I must say, it was absolutely magical experience, and especially the first time getting free reign in the lab, getting to look at all their amazing samples. They're absolutely beautiful, as you can see under the microscope here. And it was just a kind of spine-tingling experience to hold these things, which are older than the planet you're actually on, and just look at them. And as well as some meteorites from the moon, which were picked up during the Apollo missions. So it's absolutely fantastic, and I learned a lot. And then there was a kind of fateful meeting where towards the end of the training part of my internship, the person who was showing me the meteorites, Dr. Richard Greenwood, pulled one last sample out of the drawer of the Chelyabinsk chondrite. And this immediately was exciting to me. Some of you may actually have heard of this meteorite, although it might not seem obvious at first. It fell to Earth in really dramatic fashion over Russia back in 2013, and it was recorded in all people's dash cams. In Russia, they have cameras on a lot of the front windows of their cars, and so when this thing came through the atmosphere, it made a massive booming noise. All the cameras recorded it, so it's the best meteorite fall, best recorded meteorite fall in history. It did smash a lot of windows, the explosion from when the meteorite broke up in the atmosphere. Nobody was seriously hurt though, so I can sort of safely geek out about it. And then pieces fell to Earth, people gathered it, and there was a piece in the collection at the Open University. And the really cool thing, from my perspective, being there, was that Chelyabinsk was another one of these unusual chondrite meteorites that had deformed minerals in it, that seemed to have been deformed about 4.45 billion years ago. There are people who had just done work on it about that year that I was doing the internship, and I'd read about it. So it kind of felt meant to be. I'd done this poster all about these shock meteorites that seem to have been affected around the time of the formation of the moon. And here, one of the candidates was in my hands. So I thought, maybe I should try and do something while I'm here on this. I don't know. I didn't really know what I wanted to do, but I said, right, for the remainder of my time, Mahesh, can I work on Chelyabinsk? And he said, sure thing. So I just started looking at it with all the different microscopes that they had at the campus. And I started imaging the phosphate minerals, these key things that people have been using to find out how deformed the meteorite is and when it happened. I can tell you more if people want to ask questions at the end about exactly how that works. But this image here shows one of the pictures I took. The red dots indicate where the scanning electron microscope, that's the technique I was using to image this thing, was picking up that there was phosphorus in my section of the meteorite, and phosphorus being a key component of these phosphate minerals, like apatite, and the thing that people are studying. And I was able to find out where all the different grains were in the section that we had, and I just started looking at them to see if I could spot anything that people hadn't spotted before of any kind. Stumbling in the dark, really, but I did find something. I found that every single one of the phosphate minerals, these apatite grains, were associated with a different mineral called olivine. Probably haven't heard of it, but it's one of the most abundant minerals in the solar system. And there were these interesting textures, which to a geologist suggests that at some point, everything here was olivine, labeled with the OL there. And then it's been replaced, overgrown by the phosphate for some reason, which was just, that's what the textures demand. Again, I can explain more if people are very interested in that. And you wouldn't expect it because there is almost no phosphorus in olivine, but for some reason, it seems to have been replaced by the phosphate at some point. That's how they grew. And people didn't know how the phosphates grew, but this was a strong indication that this was important. So whilst we didn't understand it, we had a cool observation and some questions, and we published that in a small article for a conference. It's typically what you do when you have a preliminary finding. So I was pretty excited about that. And I continued to think about it even after I finished the internship, finished up my degree and went to Cambridge to start a PhD on meteorites and other things. And I came in hot with a paper, in the works and some ideas ready to test. And I thought, oh, it's gonna be fine, it's gonna be easy. And it definitely isn't easy doing science, although it's definitely worth it. So the next 2 years get pretty interesting scientifically and challenging. So things started off well. I applied even more techniques to these phosphate minerals in my meteorites. We confirmed that the association with olivine was absolutely critical for how these things first grow, how they come into being. And the other thing we found that was perhaps even more interesting and more relevant to what I was talking about earlier with the formation of the moon and finding out when these impacts happen, is that the phosphate grains aren't all the same. Some of them are very different. I mean, I'm not going to explain all the complexity of this image here from one of my papers, but essentially you can see the phosphate grains colored in here, they don't all look the same. They show different textures. They have all these subdomains, these more or less crystalline regions within them. And people until now just didn't know that that was the case. So when Yin and the people studying these things before had tried to find out how old they were, they analyzed them essentially randomly. They just went in and analyzed whatever grain, didn't know that there was all this complexity within each grain. And it occurred to me, well, maybe actually that's not the way to do this. Maybe we should pay more attention to the structure of each grain. Maybe that would tell us something different. And the reason I think that's really important is because although I've been spinning this story, which the Yin paper suggested that the meteorites were involved in a collision 4.45 billion years ago, actually there's a huge, huge amount of debate, as in science on anything, over this issue. And this is just the table I put together showing all the different proposed ages for when these minerals may have been deformed. And underlined there is the one that would correlate with, or match up with when the moon formed, 4.45 billion years ago, 4,452 million. But there's literally dozens of other possibilities if you use different minerals to try and work this out. And the question is, why is there, are all these different minerals really recording something real? Are some of them just being interpreted wrong? Is there any reason to think that the age from the phosphates, from the apatite, is actually correct? And I thought I had a really exciting opportunity because the textures I was finding in the apatite grains really demanded that at least some of them had been heated up much, much more than others. There was very obvious that some of them have had to have been associated with a big collision, something very, very high energy. And if you were to analyze just them and prove that they had this extremely old age, then you could be very confident that the meteorite did participate in a collision at 4,452 million years ago, around about when the moon formed, which would strongly support this idea that they are essentially debris from that massive collision. So that was the hypothesis. The way to test it is to use a machine that can analyze these grains on a very, very small scale, called a secondary ionization mass spectrometer. Don't ask me how it works. It's very confusing, people who specialize in this stuff, but it would allow us to analyze the grains at a very small level and work out how old they were. And so we applied for time on one of the only ones in the UK. I mean, these machines cost millions of pounds and hundreds of thousands of pounds a year to run. There's not very many of them, so it's very competitive. And we applied. And unfortunately, we were rejected. This happens a lot in science. People assume that if you have a great idea, it's just going to happen immediately. but you're up against lots of other great ideas, and every facility has its own priorities. And fundamentally, they weren't sure that they can actually do this. They thought maybe it was a bit too hard for them and suggested a different lab in Stockholm. But Stockholm, you needed even more money because it's an even better machine to execute this work. So me and my supervisor had a thought thinking, or like, oh, how are we going to find all this money? We're just as broke as anyone else, and it costs a lot of money. So we applied to something called the Isaac Newton Trust, based at Cambridge, to see if they could help us out, and we were successful. Here's an email I got back in 2019, which was really exciting. My reply, thank goodness, thinking this is going to happen. You know, we've been waiting about a year already at this point. So we sent the samples to Stockholm. All's going to be well. They're experts in doing this kind of thing. And the machine exploded with my sample inside. Nothing to do with the sample, just absolutely terrible luck. They'd literally just put it in to analyze it, and something went wrong fairly catastrophically with their machine. So nothing happened for a few months, and then they sent the sample back to me, back to square one, and said, wait till we fix it. So that's what we did other work in the meantime, and just kept our fingers crossed. But then COVID arrives, which we've all been dealing with, and this is very accurately describes my 2020 best laid plans getting destroyed. And you can imagine, you know, we were wondering, is it actually going to be possible to get the sample back to Sweden at any point, even if they do fix the machine? So we ran around Cambridge and posted it literally in the week of lockdown, and it managed to get there. And we thought, right, okay, great. At some point, they'll fix the machine and life will be good. They'll analyze it and I'll get my results. And the machine, you know, 6 months later, still isn't working. And I mean, I keep working on other things, writing up papers, trying to get the PhD done. You don't just sit around in science, but often you have to, you know, improvise. But the machine breaks again. The machine breaks again, just about as they're about to do the analysis. All my patience not really paying off. You know, I've been waiting about 2 years for these data to test this idea and finish off the paper, and we still don't have it. And this happens so much in science. So it really is, you have to be patient as well as, you know, working hard. So the machine breaks again. We ask for the sample back because it doesn't seem like with COVID, they're going to be able to get it fixed. And we think, how are we going to get this data? Because by this point, 2 years on, I was getting contacted from other groups around the world who liked the ideas I'd published and essentially were planning on doing the same follow-up work that I'm describing here. And we were beginning to panic a little bit. And so we rethought our options. We thought, you know, who could possibly do this analysis? Who's done it before? And so we literally emailed the lab that did the original Yin et al. Study back from 2014, the one that I presented that poster on as an undergrad, and it inspired the whole project. And they fully agreed. It's a long way to go myself, so we posted the sample all the way to China. And it was a stressful thing, you know, sending a sample you've been working on for 4 years, irreplaceable, all the way over the world. And it did briefly get impounded in Chinese customs as a suspicious item, which gave me a lot of, you know, literally last week I was stressing out about that. But then on Tuesday or Monday, the sample arrived, and the lead scientist is preparing to do the analysis as we speak, which is very, very exciting. So, you know, hopefully in the next few weeks or months, I will find out if I'm right or wrong, you know, whether or not that age proposed by the Yin paper is actually the best one to be associating with when these asteroids were bashed into by perhaps fragments of the Earth-Moon collision or not. It could be either way. And that's the exciting thing about science, is you test ideas and the best idea survives. So I can't wait to find out what happens. And that essentially brings me to the end of what I've prepared, and I hope you'll find it interesting. Hope you agree that meteorites are cool, and I'd love to take any questions. But I will say I don't just work on meteorites. I also work on the origin of life and planetary science in general. So hit me with anything that you've got on your mind. Yeah.
Thanks a lot, Craig. That's yay! We're actually clapping. You can't hear us, but we're actually clapping. You've got
no idea if that was on time.
Here we go. Can you hear that now?
Well done. So actually, we've got questions from the audience. So if you don't mind us kicking off straight away, so we will start off quickly with YouTube because there are less there, and we've got a question from 9-year-old girl, and the question is, how many different types of meteorites are there?
So the real answer to that is we don't know, because the solar system is a huge place, and mostly all we have to work with are literally pieces that are randomly, they're floating around the solar system, and some of them happen to hit the Earth, and we pick them up if we find them. Most of them land in the sea and are never seen again, or in like some hedge or something. Very few are actually found in time to not be ruined. And most of the meteorites, or most of the asteroids, they're only called meteorites when they land on Earth, will never come to Earth. We'll only discover them if we go there. But as of right now, I think there's hundreds of different subtypes, but it's probably thousands. Yeah.
Thank you very much. I hope that answered the question. Then we've got another one, which is, how big was the Chelyabinsk meteorite?
That's a good question. I think it was a few dozen meters across at the time, and then it exploded. Like partially these things vaporize as they come through the atmosphere, and then it did what's called an air burst. So that's pretty lucky that it didn't just smash right into the town. It exploded in the air above it, and pieces went everywhere, and then everybody went up and picked it up. If they hit the ground, it can be a lot worse. There was a famous one called Tunguska that also fell in, I think, Russia. They love meteorites there.
Yeah.
And it destroyed a whole forest. There was no one there. Somebody just turned up one day, and the forest was just flat. All the trees were falling over. So, a little bit scary if they're quite big. But it was quite a small one.
I see. Oh, so now we know the name of the girl, and that's Ania. So thank you very much for watching, Ania, and we're glad that you're happy to have the question answered. Now we've got a question from Daniel, which is, what's the stacking process for micrometeorites like this? Is it similar to DSO image stacking?
Stacking the micrometeorites. Say that one again?
Yeah. So the question says, what's the stacking process for micrometeorites? Like, is it similar to DSO image stacking? I think this is about taking a picture of a night sky, if I were to take a guess. So maybe we're talking about meteorites that are far away, that haven't landed yet. I don't know.
Okay, so the way I can answer that is to say that it's very, very hard to track asteroids as they come in if they're small. So the sort of thing that I would end up working on, you will never ever see it coming. So literally for Chelyabinsk, they didn't know it was gonna land. They had no idea it was coming. They were tracking something else that was a bit bigger on the same day that was gonna do a near flyby, and everybody was thinking about that. And then on the same day, Chelyabinsk came in completely unobserved. So I don't know much about observations in that sense, because the sort of thing I work on, you can't see until it arrives.
Oh. Does it mean, I'm sorry, that's good. That's a silly follow-up question from me. Does it mean that we have there is a non-zero chance of us missing something large coming toward the Earth, or is it rather unlikely?
The large things are much easier to spot, as far as I'm aware. But I think the biggest risk is from the small things, because they're much more common. And you could imagine if Chelyabinsk, for instance, had come in over New York, imagine it comes in over New York rather than some rural town in Russia. All the glass and all the skyscrapers is smashed, the whole city. So, these things are dangerous as well as interesting. I don't think much work is put into thinking about this. I don't know. I'm not entirely sure how you would protect New York from a small meteorite. I have no idea, actually. Somebody should think about that.
We should switch gears.
I actually have a question before we move on to Slido, if that's all right.
Yep. Go ahead.
So you're waiting on the results from the lab in China. Do you have two different versions of your paper written? One that's my idea is right, and one is it's not supported by the data.
If only I was that organized, Johnny. And if it was that binary, but what if it's a mixture of both? What if I'm right and wrong? That happens all the time. I've just this week as well resubmitted after some revisions the sort of first part of this work on the observations without the ages. So I think the follow-up write-up from this will be fairly easy in comparison, because as you say, I'll either be right or wrong, and I'll just say that. I don't think it'll take as long. Hopefully not, because the last one took about 2 years to write. I came into the PhD thinking papers were easy to write for some reason, and they are so not. It's
They're
the
so
most
not.
brutal thing. It's fun, 'cause I do like writing, thankfully. If I didn't like writing, I think it'd be a struggle. Yeah.
So if we can move on to Slido, there are still several questions to ask. Let's see if we can get through them. So the first one is from Zach and Sam, age 9, and the question is, what is the most interesting you've discovered about or on meteorites?
That's a good question. I think I heard that one before we even started, and I'm still trying to decide what the most interesting I found is. I think, to be honest, the most like awesome observation I've made so far, where I just sat back and was like, that is extremely cool, was that picture I showed of the deformed apatite grain with it transforming into a different mineral, which can only happen at really high pressures and temperatures, and hadn't finished doing it, even though that only takes like a split second because it cooled down so quickly. And to me, you know, I could tell that almost immediately just from seeing the image. And it was just like a spectacular insight into what this rock had done billions of years ago. Yeah, what extremely cool moment. It's great in science because most of the time you have to sort of piece things together and it's really complicated and difficult. And that I saw the image and I knew what I was looking at. It's really cool. So I think that was a good moment.
Awesome. Thank you. The next question that pops up is a bit more technical, and it comes from Bella, who asks, what was the most recent meteorite that fell into Earth?
Oh, that's an absolute killer. I have no idea, because they fall all the time.
Yeah, it depends probably what size, right? We're thinking, because small
so
things.
Like, so micrometeorites down to dust are happening all like every second. I guess there was actually one that people saw come in that left a sky trail, only I think a few weeks ago. I think it was in Costa Rica. I think.
Did it, but it made it to the ground, correct?
Yeah. So usually pieces will fall off as it's coming down, and when they land, the area in which the meteorite pieces are found is called the strewn zone, like things strewn around. And so if a meteorite comes down in your area, there's this big hunt. Everybody gets into it. It's like an Easter egg hunt. And you'll walk around and everybody picks up every rock ever. And the actual scientists are like, this isn't a meteorite, mostly. And the official term for that is a meteorite.
Oh, no, they didn't.
That's the official term. That's scientific.
You should never trust scientists to name things.
You're wrong. I'll remember that. If there is something that the audience will take away from today, it's that there are meteorites and meteorungs.
and always be on the lookout, you know? Yeah.
Okay, so sorry, but we've got another question from Zach and Sam, and I think I've asked that before we even started because they were very eager to be there before the event even launched, which is, what is the most interesting meteorite in the solar system that you know of?
Okay, so this is an extremely difficult one I was also thinking about, because meteorites are interesting in all sorts of different ways. But the one I've chosen to go for is the most historically interesting meteorite, which is called andchondrites, that fell in, I think, Germany, and it's the oldest observed meteorite to fall. So it's not the oldest meteorite, but it happened in the 1400s, and people at the time were standing outside this church in Germany and saw a ball of fire come down from the heavens, and it dig a big hole in some farmer's field, and they just had no idea what it was. This massive lump of iron from the sky, and you know, at the time they assumed it was
apocalypse,
whatever, you know, some mystical thing, and they put it in the church as like a holy stone, whatever, the holy relic of andchondrites. And then, you know, hundreds of years later, people start to ask them, what the heck is this? And people speculated, you know, there were the stories, it came from the heavens, from above, and the scientists of the day didn't believe it. They just were like, oh, it's just some weird rock. But then, you know, as we start to learn more about meteorites, actually see them falling, pick them up, we realized they were identical. And then all the crazy people saying it had come from above were completely right. So,
they were meteorites.
They were, yeah.
I'm so sorry. It's stuck with me now. Okay, I'll stop. Also, but that's a, I think that's a very interesting story.
There's a meteorite show there every year. Everybody goes to the church to see the meteorite, and they all show off the new meteorites that have fallen. It's a big deal.
That's pretty awesome. So actually, I will bump up a question that's a little bit lower in terms of likes, because on Slido they're sorted by people's responses. There's actually a question which says, which country did the meteorites fall in the most? Because you said that in this particular place they have a show. Is there any preferential location where people find them most?
So 2 parts to that question. There's no preferential place where the meteorites fall. It's random. You know, they just fall wherever, all across the Earth. There's no specific place where meteorite, because they're coming in from all directions. But there is specific places where people go to find them. And that's because it's much easier to find a meteorite in some places than others. So the 2 big ones are the Sahara Desert, right? There's nothing else around, it's just sand. And if you find rocks in there, there's a better chance than not that they're from space. Whereas anywhere else, it's very hard to, you know, pick up a rock, and, you know, why would it not just be from there? And the best one, well, it's much harder to get to, even more so than the Sahara, is Antarctica. People go on expeditions to find meteorites all the time. NASA, people like that. I know some people who have done it. You train for quite a long time. It's like going to space or something. Spend months training, and then they go down and spend months on the ice. And it's because on the ice, where are the rocks going to come from, apart from falling from space? So if there's a rock just lying in the middle of this massive glacier, you've again got a decent chance that you might find a meteorite. They usually come back with a few hundred. So I don't think I'll ever do that, though. I just don't think I can be bothered. Great meteorites from like any museum, and we've barely studied any of them. So, but yeah, it's good job for people that do that. It's fun.
It's commitment for sure to go through all the training, like go to.
And they get the best meteorites, right?
Yeah.
So I think there are, let's just say, 2 more questions that that roughly sum up all the other questions in the bunch, I think. And the first one that I would like you to take a look at is, or listen to actually, cheeky. Do they have any traces of the meteor that they think caused the extinction of the dinosaurs in the Yucatan?
Yeah, so that's another good question. And the answer is that they don't have any, there's nothing left of the meteorite itself that came down. It was so big and it came in so fast that it completely vaporized. As you can imagine, it killed off all the dinosaurs. But the reason we know that a meteorite even did this is because it did leave behind some evidence that this event happened. And that's in the form of both a gigantic crater in the Yucatan Peninsula near Mexico and South America, now mostly filled in with mud under the sea, but you can go and see there's this gravity low, they call it, they map it, where there shouldn't be anything, and there's something missing there. And they think that that's a large crater. And then the other key piece of evidence is that little tiny pieces of the vaporized meteorite were distributed across the whole Earth and came down from the sky, settled out into the soil, and became part of the rock record eventually after millions of years. And you can find many places on Earth this exact identical layer of ash and dust that fell down, which contains very high abundances of an element called iridium, which is very common in meteorites, but not at the surface of the Earth, because it mostly ends up in the core of a planet when it's forming. And so if you have a whole meteorite come in, the core gets vaporized, everything goes everywhere. So there pieces of the meteorite are found, and it's how we're able to know that it came in at all, but not like a lump of this thing. Nothing intact survived.
Thank
Really
you.
cool.
Yeah, that's fascinating.
That's awesome.
So actually, we were talking about meteorite composition, and I think there have been, well, there are several questions that roughly touch up on the same thing, which is what the meteorites are made of, why are they so colorful, the ones that showed pictures of, and yeah, mostly about their structure and how large they can get. So if you don't mind summing up in a couple of words what the structure
Well,
meteorites
The key thing is what they're made of is they're made of extremely similar stuff ultimately to rocks that you would find like outdoors right now. If you're just going to your garden, like pick up a pebble. They're mostly made of silicon and oxygen, these elements, and other things like magnesium, calcium, iron. And the minerals can be very similar, like feldspar, it's one of the most abundant minerals in the Earth's crust, and it's found in meteorites, and olivine, very, very common. If any of you have heard of basalt, it's a common rock full of olivine, and you find that in meteorites. And the reason they were so colorful is because rocks in general look very different if you slice them very thinly and put them under special types of light on a microscope, and the light gets diffracted, moves around, some of the wavelengths are destroyed, and you're left with fancy colors. But the reason we do it is because it helps us work out which minerals which very easily. But it looks amazing. But all rocks do this. Rocks are actually very beautiful on the inside.
Oh, what a pun. All right.
And I think, was there one more bit to that? Was it like, how big do they get?
Yeah. Well, the question's on the size of like, what is the largest meteorite in the solar system, or how big they get.
So once again, so they're called asteroids before they fall to Earth.
Very good
So
point.
this sliding scale. I mean, it's all just space rocks, right? And Earth being the best space rock. So planets are space rocks, and then you go down through planetesimals, asteroids, and then tiny little pieces flying around. So the biggest is Earth.
that was fairly profound, but space rocks.
Yeah.
Cool. That's I haven't thought of Earth as being a space rock because it has the label of a planet, right? So
yeah, it's a space rock, the biggest and best.
Just a rock.
Just a rock. Righto. So I'm quickly checking YouTube. Yep, no more questions on YouTube. So I think at this point we can say a big thank you to Craig for an amazing talk, and B, your answers to your questions. I think all of us here actually learned a lot from it.
Oh, yeah.
So a round of applause. And at this point, for anyone who's still with us and would like to join, we've got a quick game of theory versus myth that we launch on Slido. And funnily enough, I think all of us, the committee, when we were coming up with those questions, we actually weren't sure whether some of these things were theory or myths, so we had a lot of fun as well. And I've just launched the quiz on Slido, and because we have a little bit of an offset between us and the audience, so we'll give people time, and we'll also give me a moment to launch the presentation. Hopefully, I did. And me.
Well done.
There's a cat in a tinfoil hat. And I decided to rip up the name of a very popular Discovery show. We're called Astro Busters now.
What do you mean? That's totally original.
I'm trying too hard to be funny.
Alright.
Craig, I'm hoping to see your answers at the end. We're going to ask you how many you got.
Why though?
It's a good question.
It's a very good question.
I'm not going to insult myself in public view.
No, that's perfectly fine. You can. That's what the game is about. You can just enjoy. I feel that's the whole point. Okay, so since sorry, I don't know if many people stick around for the game part of today, given that. So we've got numbers ramping up, so there are people sticking around. But so let's kick off with the first question. It is illustrated with the sun, and the question, the fact myth or theory is the chemical composition of our sun is the same as that of Earth, since they both came from the same source. And oh my god, 100% of people saying that this is myth. Everyone is unanimous.
How many people have voted though?
6. So that's already a
Oh.
significant number. It's not one person voting.
I was going to say 100% of one vote. So
Oh, it's a little bit like elections in Poland. Sorry. I don't know why I made that reference. Okay. Oh, and I forgot to switch the slides in the presentation. You know, yeah, it's not that easy. Trying to manage all of it if
you're
you're
doing really well. You're doing better than any of us could do. So
that's fine. That's perfectly fine. Okay, so everyone out of the whole of 6 people say it is a myth. So let me switch back to the presentation and check whether it is correct, assuming that I've done the presentation correctly. And yes, it is correct. It is a myth. But actually, it was a real theory that people believed. I can't speak English. All the way until Cecilia Payne Gaposhkin came into the picture when she did a PhD at Harvard. She studied spectra of stars in the Milky Way and said that what you see in a stellar spectrum, i.e. the intensity of light versus wavelength, what you see in it, there will be dips, there will be troughs and peaks, and she argued that the intensity of those troughs does not mean that different stars have different chemical composition. For example, one of them is made of iron and the other is made of helium. She argued that this is not the case. She said that they have similar composition, but they have different temperatures. And because of that, she identified Sun as being primarily made of hydrogen and helium, rather than the same composition that we find on Earth, which very nicely ties into Craig's talk, who said that, well, definitely helium and hydrogen were not the principal components of our Earth's crust, right? So yeah, people did believe that Earth and Sun are the same thing. It's just that Sun is hotter, so it shines. But Cecilia Payne came along and said that this is not the case. So we've got another question. If I can only manage Slido. And the question is, Mars is covered in a series of geological structures dubbed Martian canals. And because I've set up this question, I've also decided to add a third answer. So we've got real theory, myth, and the third answer is surely there are also Martian gondolas. I'm sorry.
That was a pity laugh.
Well, at least you did laugh. There is no one responding so far. I think people got tired of my jokes and they decided that's time to leave the stream. I would not be surprised at all, actually. I'm not even kidding. But yeah, that was a cool thing. Actually, let me real quick check what question is next. Ooh, Haley, would you like to take up the next one?
Oh, I can't see what it is. What's the next one?
That's number 3.
Oh, right. This is the one that. Wait, are we done with the Mars one?
No, we're not. It's just I'm asking whether you'd like to take it up.
Yeah. Let's do it.
Okay, cool. But we're still waiting for answers for the Mars one. No one's responding. I don't know how I've set up the quiz. Maybe people can't answer before I. Has any one of you guys checked the quiz? Because I've launched it.
It says voting is closed.
Oh, sorry. So that's my that's me. Can I fix it right now? Or not?
Yeah, voting in progress.
Okay, thank you.
Yeah.
Sorry. So that was me, but that's okay. It's not like I've done it 1,000 times now and I still managed to.
People trying to vote, the machine's not voting. Asha, why are you perpetuating voter fraud? This is not good in the current climate.
Yeah.
These are illegal votes.
Well, at least these aren't posted.
We only allow legal votes here.
Okay, so since we've got a couple people who've already responded, I'm sorry about closing the votes. We've got 6. I'll take that, and we've got a very nice split. Oh, someone voted for the gondolas. I'm really happy. Thank you.
Someone likes your joke, Asha. How does that feel?
It feels very good.
Ooh.
You can't disprove that. Can you? Can you disprove that?
So actually,
there are no gondolas.
there are no gondolas. Yeah.
That's the 3.
I think we can prove that, actually.
Yeah, I think we have high enough resolution. So funnily enough, 50% of voters said that this is actually real theory. And this is wrong, because the whole point of Martian canals, not because they had gondolas, but it's because people, when they saw the image of Mars in low resolution through their lunettes, they saw structures that resembled canals. And the image I'm showing right now in the presentation is a side by side of Mars and roughly the location where people thought the canals were observed. And if you look at the pattern of patches, like dark and bright large-scale structures on Mars, and if you close your eyes, squint, that word?
Squint.
Yeah. So if
Don't
you do
close your eyes, squint.
yeah, if you squint, if you do this and look at the two images, you can actually see that there is a lot of similarity between the two patterns, and that's why people thought there were canals. And people actually thought that they used to be like abandoned structures left by intelligent life. So for the longest time, Mars has inspired people to believe that there used to be that Mars used to be just like Earth, full of greenery. And people thought that these canals were used to transport water in between, if you will, green areas on Mars by an ancient civilization, which is a pretty cool idea. But then telescopes actually got better, and then we realized, oops, that's no longer the case.
Actually, there. So it just was like an optical illusion or something, right?
Yeah, just an optical illusion, exactly. Like many things with the theories, as you will see, many of those myths are actually theories that could have genuinely been true according to the understanding back in the day.
Sure, yeah.
So I've just opened another place, another question for voting, and I've illustrated it with a presentation that has a superluminal jump from Star Wars. And the question is, can you read it out, please?
Yeah, so this one is cool. Is it possible? Oh, it is. The statement is, it is possible for matter to travel faster than light. Myth or theory? Dun, dun, dun.
I don't know why I'm so excited.
This is a cool one, and I actually learned something on this, so I'm going to try and explain it when we get to the end of the quiz.
Okay. We've got already 5 answers in. This time I didn't close the voting.
Well done! Yay!
Movement.
Oh, actually, so as we're waiting for the answers to come in, Craig, if you don't mind answering one more question. So Ania, age 9, asks, why does Moon have more meteorite craters than Earth?
Good question.
So the Earth is an active planet, and the Moon is quite dead at this point. So the Earth has an atmosphere, it has the oceans, it has life forms on it, like us. It has mountains being built and volcanoes and plate tectonics. So the crust is changing and moving around. And the Moon is cold, small, dead. There's very little geological activity. So when something hits the surface and leaves a crater, nothing happens to the crater ever again. It just sits there forever. Nothing erodes it or fills it with mud or covers it in ash. So the Earth and the Moon have exactly the same number of things hitting them, but the Moon records it better. And that's why it's so useful, because it's a silent witness to everything that's happened over the last 4.5 billion years that the Earth has forgotten about.
That's thank you very much. That's very insightful, and a very good question on your part, Ania. That's very
good stuff.
That's a very good question. So we've got the answers coming in, and let me tell you, Haley, that it's 33% real theory and 67 myth.
Ooh, this is exciting.
So
I mean, I was with 67% of you. I was like so sure about this, but I was wrong. It's actually true. And I'm so mad.
Because it's about the wording, isn't it?
It's a super trick question. So a lot of you would have heard that obviously nothing can travel faster than light, but this is only true in a vacuum. So this means if you have basically completely empty space, then yeah, light is has the fastest speed of anything. But light does actually slow down when it goes through things that are nothing, I guess. Like if it goes through water or thick water or something like that, then it does slow down. And there are actually some cases in which that some really energetic particles can get faster than light in some particular medium. So this is called Cherenkov radiation. I'm butchering the pronunciation of that, but
Cherenkov, I think. But
yeah,
don't quote me on that.
Actually, no, I think it's Cherenkov.
I'm not Russian, so yeah.
Anyway, you should look it up and read about it a bit more if you want. But it's pretty cool, and I did learn something, so that's neat.
Yeah, strongly recommend. It's always blue and nice, and takes the name after the Nobel Prize winner. Right. Awesome. Shall we move on to the next question? Oh my God. You need to take that one up, Johnny.
Yeah, this is a really cool one. I like this one. So question 4 is just simply the statement: there's such thing as ice volcanoes in the solar system. Is that real, or is that just something I've made up?
Well, the image that you've provided looks made up.
It does look a bit made up, doesn't it? Funny that.
No, it still looks like a very bad game render. If there are any visual artists around here, please help astronomers.
That doesn't look real.
Well, I mean,
I don't believe you. I think this is a lie. I think you're trying to fool everyone.
How dare you? You doubt me. Oh,
of course I do. I'm imagining like a volcano like spitting out ice cubes or something. It just doesn't sound real to me.
Oh, just like those fridges where you like put the cup in and just go.
Exactly. Yeah. It just goes.
Yeah. Yeah.
Oh my God.
What have the people said, Asha?
Okay. So we've got 4 answers, and I think we're gradually losing people who are playing. I think it's my jokes. I'm really sorry. But yeah. Oh, just as I've said, I forgot that we also have a little bit of lag, so I'm not discouraged. So moving on to another thing is that we still have people watching us on YouTube but not participating in the game, which probably means that they're
disappointing, to be honest, but fine.
throwing shade on the audience.
I have no shame. You guys know this.
Oh, right. So 5 people answered it's 100% pure theory. Which is as in it being correct and not being a myth.
Yeah,
Johnny.
no, that's totally correct. Everyone's correct. Haley, the public have shown you, they've shown their trust in me. Yeah, no, it's totally correct. They're called cryovolcanoes, and we see these features on solar system bodies like Ceres, Pluto, and on some of Jupiter and Saturn's moons. Basically, instead of lava and melted rocks that you would find in volcanoes on Earth or in Io and places like that, it just spews out ice and gas that's like it's water vapor and things like that, and actually liquid water as well. And I believe the next image, the one that
it's already on,
that looks totally fair, it's already on. Fantastic. This a picture from I think it's Cassini, the NASA mission that went to Saturn. And sort of an edge-on view of Saturn's moon Enceladus with these ice fountains or these ice volcanoes spewing out some of their substances into space. It's one of my favorite images in astronomy. It's cool.
It's really cool. I really like that.
Very nice.
Yeah, that's a very well done. As I've mentioned before we even started the stream, it looks just like a picture taken on Earth, but with, say, a bad camera on a very snowy day. Or like a foggy
Start
day.
the conspiracy theories.
Oh, sorry. No. The point being, it looks amazing. That I'm admiring the technology and the advancement of human science. Okay, and I'm just speaking random words, no changing slides, you know. And we've got another question, which I thought I would illustrate with a very famous movie poster, and the question is, I'm sorry, I need to read it out. I'm sorry for hijacking this game, but heat is the flow of a weightless gas called caloric between hot and cold bodies, and that's why we say we burn calories when we exercise. Is that myth or is it theory? And the illustration is Van Kilmer, Robert De Niro, and Al Pacino in the movie Heat.
I see what you did there.
Oh, sorry.
I haven't actually heard of this caloric thing.
Really?
Yeah.
Yeah.
Well, I do remember vaguely seeing that during our undergrad in physics.
Oh, okay.
Yeah.
I don't remember anything to do with.
I'm glad that I hope that people started responding before you said that, because it now sounds like it's
No,
Oh,
I
no.
remember those like words being said. I have no idea what's the theory.
They
Like,
also
it's so
teach
vague.
us things that are true, and they teach us things that are wrong as well.
oh no. So everybody said it's a myth, and everybody's correct. But
Can't
that's
trick anyone.
no.
These guys are too smart for you, Asha.
And I was so happy with with my illustration. So yeah, it is a myth. Obviously, well, actually, it is a fairly successful myth, because they could explain a couple of simple physics phenomena with this idea. So if you have this weightless gas that has no weight but for some reason has volume, if you warm up air, it expands, correct? So that's why balloons fly. And if you think of heating up air, it would be transferring this weightless gas into the air, hence increasing its volume. So that makes sense, right?
It does.
Yeah. So it could explain a couple of simple things, but obviously it failed
But it's
dramatically
wrong,
on others.
right?
Yeah, it is wrong. It is a wrong theory. But it was.
So we shouldn't explain it like that. Just to be clear.
Oh no! Of course we can't explain it like that right now. What I'm trying to say is that back in the day, when people were really not very comfortable with the idea that gas is simply very loosely, a lot of particles at large distances from each other, moving quite fast. People didn't know that, and it made sense to them that this amorphous thing could be added to change volume of air that was expanding while being heated up. That's all I'm saying.
Yeah.
And right now we of course understand what heat is. That this is a demonstration of the internal energy stored as vibrations of the particles. But enough of that. I've put a cheeky illustration of thermal convection up on the slide. Because I'm very keen on Wikipedia images, so let's just move on and stop me from blabbering. Does anyone want to take up the next question? Since I've been talking way too much, and this is question number 6.
Oh, Haley, I feel this is one for you, definitely.
Is it?
You're the cosmologist.
Sure. Okay, I'll take it. Is the slide up?
Yep, the slide is up.
Cool. So the statement is, there is an infinite number of parallel universes which appear and vanish all the time. That's trippy.
Yep.
I don't have anything else to say.
Also, you would be proud of my illustration. It's just universe bubbles swarming around empty
the
space.
universe bubbles. Yeah. But this means there's an infinite number of copies of all of us having the same astronomy on tap, but maybe talking about something slightly different.
Yeah, like me skipping on an unfunny joke or two. For
Yeah,
example.
maybe there's a parallel universe in which Ash's jokes are funny.
Ooh.
Yes, that could also
Maybe,
be
I don't
the
know.
case.
Maybe that's a long shot.
Maybe you're a little bit too optimistic. All right, since we've got a couple answers in. Ooh. So we've got an even split among 3 answers. Well, almost even. We've got 20% people saying it's real theory, and an even split between myth and stop kidding me. Because I wanted an answer, stop kidding me. Do you have any opinions on the answer to that, Haley?
I don't know. I mean, I think the answer is like none of the above, because we don't know, and I don't know if we could ever know.
Yeah.
So that's a conclusive answer for you.
Yeah, that is true. I marked it as a real theory, but this is really far from being it is a theory, but it's far from being experimentally verifiable, and hence, yeah, I'm not sure I'm not sure which definition of theory we're sticking to. If we're sticking to the one that's supposed to make predictions.
I think like by theory, what we mean is like mathematically possible.
Oh.
So like I think there's some kind of like mathematical framework in which you can have infinite universes.
Yeah. Yeah, not to
but
mention
because
the
we
quantum
can-
mechanical world, right? When
Sure. Yeah, but because we can only observe so far, I don't think that we'll ever actually be able to see these. I'm not sure if there's any kind of signatures that could arise from these kind of universes coming into existence or something. I have absolutely no idea. But I think it's pretty widely accepted that the parallel universe theory can't be proven. It's fun to think about, but I don't really see the point if we can never prove it.
see, so that's what I meant by saying which definition of a theory we're taking,
Yeah.
because there
Yeah.
are some people who would agree that a theory is meaningless unless it can make real observable predictions.
Sure. A lot of mathematicians would disagree with that, though.
Hmm.
That's not an insult. It's just they like to do
Yeah,
maths.
that's just a characteristic of the department. Yeah. So switching gears, I don't know if there are any takers for question number 7.
Yeah, I'll do that one.
Awesome.
I do planet stuff. Let's go for it. So question 7, the statement is that the Earth is at the center of the universe, with the sun, stars, and planets all orbiting around it.
I've included the cheeky graphic you've provided. I think it's pretty awesome.
Yeah.
I really hope.
Are we
everyone
going with
gets
the geocentric or the alternative, the heliocentric?
that. Please get this right, guys. Come on.
Please get this. Yeah, this is the easy one.
This is, yeah, we're throwing you a bone. Not that you don't need it. I mean, everyone's got like everything right so far, right?
Yeah.
Yeah, they've got more right than we have.
Yeah.
See, that's what happens. That's what happens when you sit in your niche and all you do is, I don't know, meteorites, planets, black holes, and I guess modified, well, weird cosmology. Yeah, sorry, I didn't want to I didn't know which box to put you in. Simulation box. Which simulation box to put you in?
Weird cosmology.
Yeah. Do we have some answers?
Yeah, we do. And oh no, people are like, okay. So maybe it was cheeky because we've got people divided between myth and theory, and I've added a third option, which is also isn't the Earth flat, but nobody voted for that. So I think it was
well,
just
again,
cheeky.
it goes. I think it goes back to what we were saying before about what is a theory, because it was the theory back in the day, with the day being sort of the 1800s and before. Yeah. But interestingly, for your third option, isn't the Earth flat? They didn't actually think that. So in all of these models, as you can see, and the sort of the nice image that we have, obviously that's not from a historical book or anything, but like they believed that in their model where the Earth was the center of the universe, they still knew it was a sphere. So sorry to the flat Earth people.
Oh wait, so are you saying that Ptolemy? Is that how you pronounce him in English, Ptolemy? That.
Yeah, Ptolemy.
Oh yeah, that guy.
Yeah, the Roman in Egypt, right? Yeah, no, although he was a strong proponent of the Earth being the center of the universe, he knew that it was spherical. Basically, the reason they thought it was the center is because they saw everything else going around it. You know, the sun came up, the stars go round, the moon.
I mean, you can't blame them.
Okay, makes sense. Yeah, exactly. And so, yeah, there was disagreement though, as Craig said in his talk. All good science is debated. So there's actually a Greek guy in as early as 300 BC. So those ancient Greeks coming back again, as they always do in astronomy. He actually proposed that the sun was the center of Earth's orbit, with the moon going around that. I'm not sure he went as far as to talk about the universe, but certainly said that the Earth was going around the sun as early as 300 BC.
And it's interesting how one theory stuck on, and then it came back to Copernicus, who said, look, guys, let's stop fooling around. It's actually the other way around.
Yeah, and then there was the whole thing with Galileo and the church.
Of course.
It all got very political.
Yep. Very political, very quickly.
Yeah. But well done the audience.
Okay.
So we've got another statement, and I can't remember which number it is. And I've got a dramatic crash illustrating that. So I think that's one of your ballparks, Johnny. Ooh.
Yeah, I think we're to 8, is it?
Yeah.
Yeah. 8.
Yeah. So it's a statement that there used to be a planet between Mars and Jupiter, and its destruction led to the formation of the asteroid belt.
Yeah, so hands down, I had no idea. I actually didn't know anything about this before I read your response, Johnny. So that was very instructive to me.
It's
I like your
it's a
illustration.
cool one.
You
I think
can't
it's the
see
same
it.
one that Craig had in his talk, maybe, or a similar one at least.
Yep. Yeah. I've made it into a combined slide in PowerPoint. You'll be able to
Ooh.
see it once the stream is
I'll
over.
go back and have a look at it. Yeah.
Astro artist. Well, I'm kidding, of course. But okay, we've got answers coming in, and we've got 50-50.
Ooh, I like that.
Mm-hmm.
Split audience. So basically, as Craig sort of alluded to in his talk again, it's sort of true, but it's also very not true. So there was no one planet that exploded or had an impact on it that created the asteroid belt. It was called Planet 5 or Phytons, Krypton, whatever you want to call it. There was multiple theories that all suggested that it was like this one planet that was specifically in between those orbits. But actually, for the kind of size of planet, it would have to be tiny to make up that kind of stuff. So the actual theory of it goes today, or I don't want to say fact, because science is all about progress. What's fact today might not be correct tomorrow. So what our current understanding is, let's say, is that it is actually multiple collisions and multiple objects in the early solar system that smashed into each other, and because they smashed into each other, never made it to planets in the first. So it's what Craig called planetesimals earlier. So the asteroid belt is sort of a remainder of all these things smashing into each other.
Makes perfect sense.
So it's no one planet.
Yeah. Well, makes perfect sense now, but you can easily see how it didn't make sense back when people thought of it.
Yeah, definitely.
All right, moving on to the next question. Oh my god, I'm so bad at managing this. I've only launched it, sorry about that. But can I read it out because I find it quite cool? The statement is that you could host Astronomy on Tap on comments, i.e. we found alcohol on them.
That's all we need.
Dangerous. More dangerous than the pub.
Dangerous.
I don't know about right now. Maybe it's about the same.
Very much.
No COVID or any comments.
I don't know. Johnny, can you remember which comment you've used for the picture?
I think it's you got the catchy name C 2014 Q2. Yeah, but it's nicknamed Lovejoy. I can't remember why.
Lovejoy. Okay, yeah, because I thought
might be after the person who first spotted it. That sounds about right.
Yeah, because it has in case you guys haven't seen Lovejoy, well, at least that comment that we think is Lovejoy, it has this amazing tail and a very bright, how do you call this front part of a comet that's actually made of rock? It has a tail, and what does it have?
Nucleus.
Oh, a nucleus. Yeah, thank you. So yeah, so it has at least in this image, very nice bright green nucleus. All right, yeah. See, we're all astronomers, more or less.
He was getting annoyed when I called him an astronomer.
Yeah, but what I'm trying to illustrate is how varied the vocabulary is. So let's see what the answers are. And Johnny, would you like to illuminate us on what the correct answer is? We've got 60% myth and 40% theory.
Ooh, it's actually true. It would be quite hard to host Astronomy on Tap there, but if you really wanted to, you could go there, set up a presentation. You have like a lever out back to collect the alcohol, because they actually spotted over 21 organic compounds in the tail and near the nucleus in Comet Lovejoy, and one of them was ethyl alcohol, which is what we all have in our lovely pints. It would be very cold as well. It'd be a nice cold beer because it's around like minus 100 degrees, I think, in that area. So it'd be a very cold beer.
Fresh.
You know what? It
wouldn't be
like
warm.
a great business idea. True. We could, like, include some tiny amount of like another molecule that wouldn't kill you.
Yeah.
It's-
Oh, there's lots of water ice there, so you can just get some
Yeah.
water, melt that, put it with the alcohol. It's fine. Make a
I
G&T.
like it.
I think you
Yeah.
guys should sell it to Elon as
Yeah.
as an
I would
idea.
love that.
This will be our next paper, Craig. We'll do that
Our
while
next
you're waiting
paper.
for your rock samples.
Where's the
Yeah.
first one?
Yeah. Okay. Rub it in. I don't have one yet. Thanks.
No, I mean first together. That's what I meant. Oh god, that became so awkward.
But yeah, it's a real theory.
Still the next one, even if it's first.
Thank you.
So, trying to hide my embarrassment, I've just moved us on to luminous ether. Ether? Ether? What do you pronounce?
I'd say ether.
Ether.
I think it used to be spelled AE as well, so it's definitely ether.
That's what it says on the slide. Yeah.
Yeah, that's what it says on the slide, but I swear I've
Mhm.
seen just spell
It does.
it differently.
Yeah, it's just sometimes spelled with just an E as well.
Yeah.
I don't know when that changed, but
Yeah.
Well, in Polish everything sounds weird, so we call it ether with a rolling R at the end. Because
That's cool, I like
obviously
that.
it's this thing that you cannot see or feel, so it has to roll the R, right?
Mm.
Ether. Sorry, I don't know why. I'm just laughing at my language now. But the idea being electromagnetic radiation, light being part of it, travels through something called the It's spelled ether with a single E in our question, but ether with an AE on our slide. I like how consistent I am. To move between the source and the observer. And let's see what the responses are. Oh, we've got 60% theory and 40% myth. Can someone elaborate on that? Who would like to reveal the correct answer?
yeah, I
Sure.
can do. Oh, you can do it ahead if you want.
Sure. Well, this is not true, but people thought it was true because we thought things like sound waves needed some kind of medium to travel through, and obviously ocean waves have a medium to travel through. So we thought that light waves also needed a medium to travel through, but due to several quantum mechanical things, it doesn't. Was that a good explanation?
We're an educational channel. No, no,
I
but
think you guys have some more details in the actual doc. So Johnny, you want to go over your?
no, but jokes
Yeah.
aside,
So there was
okay, go on,
there was
go.
the actually the experiment that disproved this. So it was a really popular theory in sort of the 1800s until Michelson and Morley disproved it basically. And Einstein, I can't remember the exact quote, but he said they made us all look silly, and that's why we went away and we made special relativity. So thanks to them to making us look silly, which is it's quite a nice quote. It sums up science sometimes. You have to admit you're wrong to make progress.
Totally.
But basically in this experiment, they thought that because the Earth is moving around the sun, as we established in our question earlier, that basically the Earth is moving through this ether or eder. And because we're moving through it, if you have light in two sort of perpendicular axes, if you measure the light between them, how fast it's going, it will be slowed down in one of these directions more than the other because it's going against this movement of the Earth. And they found no difference. They found that it was going exactly the same speed in both directions. They're like, there can't be any ether. Yeah, it was a pretty cool experiment.
Yeah,
Really
but it was
smart
set up.
setup.
But it was set up to actually not. Was it set up to disprove it, or was it set up to check
No, it was set up to prove it.
to prove it exactly?
Yeah.
That's
Yeah, exactly,
That's the
yeah.
best part about
Sorry.
it.
Yeah. So they went this like, right, we're going to prove this theory. We're going to show that we're all right, and then they
We're
did it.
meteor
They
wrongs.
found it was wrong. Yeah, the meteor wrongs exactly. Oh dear.
No, it's stuck.
Let's
it's
move
stuck
on to the
with me.
next one.
Yeah, the next one is already up, and I love your illustration.
I
Given
didn't draw this. I found it on the internet.
yeah, but
just
it's a very good
before.
find. So
I do like this. It's quite good.
yeah, our screen is bright yellow right now, because of the background, which is fantastic. We've got Einstein holding or shall I say Einstein? Anyway, Einstein holding E equals mc squared sign and being angry, like battle royale against Newton who's holding an apple. I think it's a great illustration. And the statement is, I'm gonna steal it from you, Johnny, but then anyone can chime in at the response. Newtonian gravity is wrong. Einstein's general relativity is the correct theory. So that's the statement. And the question is that a correct? That would be theory, or is it a wrong? That would be myth. Response. And people are slowly responding to that. Apart from a very good graphic, I feel like this is a topic that's often misunderstood is probably the wrong expression, but it's something that you learn at school and you're presented with as a fact without thorough explanation, especially if you're not a physics major. You just go through life you just go through life with a set of physics facts, and I think a lot of how we view this particular question depends on what our physics teacher in our middle school tells us. So I'm just wondering what the audience understanding is right now. And I'm keen to hear your answers. So
if anyone wants to hear more about Einstein versus Newton, there's a really good video on this YouTube channel done by me.
Excellent plug.
Shameless
Excellent
plug.
I thought you were going to mention rap battles of history.
I wasn't, but I don't know what that is.
Okay.
Link in the description from Craig.
No, but seriously though, the audience is divided between we've got 75%. Well, it's only 4 people who responded, so it's 3 people who said that it is true that Newtonian gravity is wrong. 1 person that said that this is correct. Well, no, 1 person that said this is false, and nobody said that this is both Newton and Einstein are cool. And what I meant by both Newton and Einstein are cool is that they're both right in a way. So I would like to hear your opinions, guys, on that, especially yours, Haley. We do refer to the shameless plug because it's a great talk. But if you don't mind summarizing it in a couple words.
Sure. So I'm going to say this question is almost exactly half correct and half wrong. So the part that's wrong, I would say, is the statement that Newtonian gravity is wrong, because that's not quite true. But it's completely true to say that Einstein's GR is the more correct theory out of the 2. Newtonian gravity is not wrong, but Newtonian gravity turns out to be a really good approximation for Einstein's gravity under particular circumstances. So this is mainly on small scales. So like on Earth, like if you throw a ball in a particular direction with a particular force, Newton's theory will tell you almost exactly where it's going to go and where it's going to land and how fast it's going to go. But if you want to look on like really large scales in cosmology, or you want to look at something like a black hole that has a really strong gravitational field, then Newton's gravity can't do a very good job. And there are many different reasons for this. One cool one, which I want to say, is that Newton's theory is based on instantaneous action. So what this means is that light travels at an infinite speed, so things happen instantly. But in Einstein's theory, light travels at a finite speed, and so things take time, information takes time to travel, which we know is true. So that's one of the key differences. But again, if you want to know more, check out my video.
Like and subscribe. Right?
Well, that's true.
Like my channel.
No, like and subscribe. Seriously though, I'm gonna quickly flash up the image of the cat in a tinfoil hat. Which says see you next time, because I found it very cool. And we're back to our Zoom call, and at this point, given that we've promised Craig it's going to be an hour, we're half an hour over, so apologies, Craig. Thank you for being patient and staying with us throughout all the time. Thank you for your wonderful talk. I think the audience really enjoyed it, given the number of questions both in YouTube and in Slido. Thanks to everyone who joined us today. It was great seeing these numbers. I think this time we've done a better job at advertising because we had higher numbers of views, or maybe people just decided they liked our series. So stay tuned for our December version. I think I'll say goodbye.
Bye.
Bye.
Bye. Thanks, guys.